Welcome back to Material Science and Metallurgy course, and myself, Dr. Avarun. And in this video, we'll be discussing on mechanism of crystallization. But before we go into the mechanisms, let us quickly go through different atomic bondings that we have. So atomic binding is what describes about the different types of crystal structure in the solid state, how they are in geometrical arrangement. And here we have primary bonding and secondary bonding. Primary bonding such as ionic, covalent, metallic, and secondary bonding like van der Waals forces and others. So let us quickly go through one by one. Ionic bonding is transfer of ions, whereas in case of covalent bond, we share it. And here comes the important one, that is our important discussion, that is metallic bond. All the metal in the periodic table have this metallic bonding between them, and which is nothing but we have a pool of electrons flowing in a positive metal ions. And here we have the secondary type of forces, which are called van der Waals forces. Now, all right, so let us understand this atomic diameter. So when you have two atoms, assume that they are at a infinitely far off distance, they will not have any influence on each other. But as the distance comes closer, the atom starts to experience both attraction and repulsion. So the both opposing forces they experience, and they cancels off, and there will be a net zero or a uh, resultant force which is at a equilibrium of both attraction and repulsion, and that distance between the two atoms will decide that interstitial distance. So that's how the atoms are in the entire crystal lattice structure at a perfect cubic, and that's is how we get different crystal lattice structures that we have discussed in the previous discussions. Now, moving forward, what is this crystallization is all about? How does they form from this atomic crystal structure, and how do we define it in terms of the crystal formation? So, when it comes to the crystal formation, it all starts for the metal to at a liquid molten state, and as it cools to room temperature. So always in metallurgy, we try to understand its journey from liquid molten stage to the room temperature. So during which we start with liquid molten metal. So let us assume that in atoms are now in the liquid molten stage. So we all know that at liquid molten stage, the atoms are having lot of energy. Atoms are very much excited and they are not stable. That means atoms move randomly here and there, and they will not having any definite crystal structure. So here the crystallization starts with the formation of nuclei. So the first thing that it occurs is as the temperature cools down to a somewhat stable one, somewhat favorable conditions, then there might be some instances or some cases where the atoms may have a definite crystal structure that which it is going to be after solidification. Mark this word, there might be an instance in all the places at some locations in this liquid molten material where atoms may have a definite crystal structure as which it is going to be in when after solidification. So that will be the starting point. So this is called nuclei formation. So those atoms have two possibilities of making it stable. One is they might be because of high temperature, they may not be stable. The other case is the number of atoms which it is made of. So as the temperature is becoming cool and more towards the room temperature, stability arises and atoms will start to become more stable. So there is a dependency on temperature. Another one is the dependency on number of such atoms from which it has formed. Suppose if it is with fewer atoms, even one atom is removed, then it becomes unstable. So when the number of atoms are more, it becomes more stable. So higher the temperature, greater is the kinetic energy of the atoms and shorter is the life of the group. And when the temperature of the liquid decreases, atom movement decreases. So lighter is the life of the group and more group atoms will be present at the same time. And when you have both kinetic energy and potential energy, the kinetic energy is related to the speed at which the atoms move. That is the atom movement. So it's a function of temperature. Higher the temperature, more active the atoms, and greater is the kinetic energy. Unlike on the potential energy, the related distance between the two atoms. That means greater is the average distance between the two atoms, greater is the potential energy. Now, let us consider a pure metal. Why pure metal? Because pure metal is made of only single element. So when you have a pure metal, the atoms will have a freezing temperature. That means freezing means from liquid to solid. So that freezing temperature for both liquid and solid state are same. Whereas the kinetic energy of the atoms in the liquid and the solid are same, but the significant difference is observed in the potential energy. This is because when the atoms are in a solid, they are much closely arranged, and the solidification occurs with the release of energy. Therefore, the potential energy is between the liquid and solid state, known as the latent heat of fusion. That is the reason why we can observe that there will be a certain amount of undercooling needed in order to release this difference of energy. So when you have this undercooling, only then we can have a stable nuclei formed. So first thing so far, whatever we discussed is about the stable nuclei formation, and later on, once the subsequent release of heat fusion is observed, then slowly there will be uh, more and more around the nuclei, some more atoms are present, which may either join to the existing nuclei or they may form their own, depending upon whichever is the favorable condition. Thereby, nuclei will move forward with the formation of a dendrite structure, which is nothing but a tree-like structure. So these dendrites are observed in the later stage of nuclei. And subsequently, when the dendrites are further solidified, they grow and form into a grain. And in the grains, one grain growth is restricted by the neighboring grain. That's how grain to grain you have different orientations and different growth. So this dendrite is not along one direction. It can be growing along various different in the three-dimensional axis. So this growth is further seen in the form of grains. So grains are growing along different axes, and one grain to other grain, the only difference is in their orientation of their axis. And the last thing that is the to solidify is leftovers in the grain boundary. This is a mismatch between one grain to the other, and grain boundaries are the last things to solidify. So finally, you can see here in this case, we can clearly observe that it starts with the nuclear formation and they grow into dendrites. And these dendrites are growing along different orientations. And finally, grain boundaries are left out and grain boundaries are solidified, the inner core. So this is how we can understand the crystal formation, mechanism of crystallization. So mechanism of crystallization deals with nucleation, dendrite formation, and crystal growth. So that's all from this video. See you next time.